Welcome back, Quantitative Analysis 2 students. Great job on exam number 2. Let's carry on with our studies for the third unit in our semester this term. Is going to be chapter 12, where we start studying integrals, and we're going to do integration. Today, we're going to focus on indefinite integrals, just an introduction, and then we're going to show how the power rule applies to integration. Integration is the opposite of derivation, meaning if you have a function and you know how to take its derivative, which is what we've been studying all this time, if I gave you the derivative, could you tell me what the original function was? And often it's something of a jigsaw puzzle that you can look at it and squint your eyes and think, yeah, I think I know what it is, and come up with it. But there are, of course, concrete rules, just like there are concrete rules about differentiation. And it actually is just the same feeling as differentiation, but backwards in every way. Instead of subtracting one, you're adding one. Instead of multiplying, you're dividing. And all the things are all opposites. So I want you to look at today's lesson and integration as a new operation, kind of like how you've learned about plus and minus as a pair, they're opposites. Multiply and divide are opposites. Logarithms and exponents are opposites, right? And of course, integrals and derivatives are opposites. So basically what we're doing today is we're going in the reverse direction. Everything that we've learned, now we're talking about what is it like, as if it was Jeopardy. Here's the answer. What was the question? Okay. Before we start talking about all of the math behind it, let's talk about the beautiful artistry of the actual symbol. The integral looks like something you may have seen in music. Take a look at our violin up there. That violin has two holes in it. If you look very closely, they're mirror reflections of each other. So really, let's look at the left hole. It looks very much like an integral, and it's called an F hole. That is the official term for that part of the violin. And it's called an F hole because, of course, it looks like an F. Take a look at it. It looks like the lowercase f in a cursive script in some way. Anyway, the way integrals work is I want you to consider it like an integral is really not just the actual symbol, but a little bit more than that. When you're taking the integral of something, what's happening is you have an actual derivative in front of you, and you're trying to find out what the original function was. To say, I'd like to find the integral of that derivative to get the original function, you need to include this piece as well as this piece, okay? And the reason why is because, do you remember when we were talking about derivatives, how important it was to stress that it is with respect to x? Or sometimes it's with respect to p, or whatever the different different examples we did with quantitative analysis and cases with economics and such, but whatever it is, there was always a specified variable with respect to that was in question. When it comes to the integral, the same thing is happening. You have to include what variable it is that is most important. In this case, when you say dx, that means with respect to x, in the same way that you're taking the derivative of a function with respect to whatever. So when you write the integral symbol, say you have an algebraic expression and you want to integrate it. When you write the integral symbol, that's not enough. You have to write dx at the end also. And the thing in between the integral symbol and the dx is that derivative that you're trying to figure out what was the original function. So also on the integral, there are these little interesting pieces I want to point out. You have right here this letter and this letter. These are usually numbers, and these are called limits. And the idea is, after you find the answer, please substitute in whatever the top number is and find out what that quantity is. It's going to be a number, right? And then do the same thing with the bottom number, put the number in and find out what that is, and then subtract them. That's going to happen when we study definite integrals, which is actually tomorrow's lesson. Today, our lesson is about indefinite integrals, meaning integrals that don't have limits like the a and the b that you see here. So today, we're not going to talk about doing any integration with limits like a and b in the pink ovals that I have here. But when we get together tomorrow, we'll do some cases of definite integrals, which means you're using numbers and substitution at the end. It's basically just an application, meaning you're augmenting the process of finding the integral, which already was a task, and now that you have your answer, substituting in numbers and doing more math to what you just got. So it just kind of makes the work a little bit more, takes up a little bit more time, but it is ultimately elementary math. At that point, when you're putting the numbers in, it's kind of just a PEMDAS situation again, back to like ninth grade. There might be fractions or decimals in it, but you could deal with it, and it's old school stuff. What you're really learning about is how to integrate a derivative back into its function, and the concept of the integral symbol, which can also be called the integrand at different times. The function itself is called the integrand in this model. In different textbooks, they have different words for what the different things are. Just as an FYI, if you pick up a calc book from high school, or for example, this quantitative analysis textbook, the word integrand is kind of used differently sometimes. So I wouldn't really stress too much the actual vocabulary here. It's interesting, but it is just trying to kind of give you the idea of what you're doing. It really would be even better if instead of saying f of x, it said f prime of x. So every model is questionable in my opinion. The point anyway is this is the general mechanics of how integration works. You have an algebraic expression. It represents the derivative of some other function. So your goal is to find what that original function was. And there are techniques to do it in the same way that there are techniques to find derivatives. So let's talk about those techniques. First, how would we come up with techniques like that? Well, in the same way before that we had our derivative rules that came about because of trial and error, meaning using that complicated limit formula with the difference quotient, and then we started to see the pattern, right? The same idea is going on here if you just observe derivatives. So for example, if you see right there 3x squared, example 1, if you think about it, you might be able to figure out what the original function was, such that when I took the derivative of it, that's what I got. Let's take a look at what that might turn out to be. Let's see if I can get this clear for us. So right now, friends, if you look in the top right where it says view, please change it to speaker so that way you can see. There we go. So that way you can see the chalkboard is the main thing. All right. So here's the question that we're asking. All right. The question is, if f prime of x equals 3x squared, then could you figure out what f of x was? Right? And of course you could. I mean, if you just experiment, some of the easiest ones have that pattern where this number and this number are right next to each other, 4x to the third, 10x to the ninth, and such and so on. And you might think, oh, well, let me just do some experiments. What about like if it was x squared? Well, the derivative of x squared, I know that's 2x. How about the derivative of x cubed? And after you just experiment, oh yeah, that's it. I guess that implies that f of x must have been x cubed, right? So does it follow? Yes, but how did I get that? So if you start trying to relate the different quantities in the story, like you have 3x here, and you could consider that maybe if I took that 2 and added 1 to it, it would give me that 3, right? And then if I actually divided out that 3, maybe it would kind of get to this, which brings us to what the actual integral formula is. Let's take a look at it now. Here it comes. So if you're going to find the integral of something with a power on it, then all you got to do is basically take that power, and instead of subtracting 1 like you used to, add 1, because you're going in the opposite direction. So just observe with me, friends, right here where it says x to the n plus 1 right there, and how you're dividing by n plus 1. Before, you used to multiply by n minus 1. See the opposite in there? And the same thing with it. It used to be x to the n minus 1. Now it's x to the n plus 1. So knowing that, if we have a case where I know what the actual derivative was, I can come backwards and get the function that way, which brings us to example 2. Example 2 is if f prime of x is x cubed, then what? Well, let's say we got something like this. F prime of x equals x cubed. Then what was f of x? So if you were given this backwards puzzle, like if it was like a trivia question, you're trying to get the answer, the way you would think about it is, well, I'm actually going to have to integrate this function to get it. So I can rewrite this idea of here's the derivative, what's the original function, to say the integral of x cubed dx. That's what I'm trying to figure out. And that will be the answer. So there is a formula. The formula says if you know what the exponent is, that the integral of x to the n dx, okay, can you see that? Yes, okay. The integral of x to the n dx, we're going to think about n plus 1. So it's going to be x to the n plus 1 all over n plus 1. That's the answer of what the integral is. Now, there is something else I'm going to bring up right now. It's plus any constant. And I'm going to explain that in a minute. Like, hold on to that idea for me for a minute, friends. Okay, we're going to come back to that in a minute. But for now, I just want you to think about if I did take the integral of x cubed, how would I wind up getting it? It would be take the number 3, consider it as n. What is 3 plus 1? It's 4. So this should be x to the 4 over 4. Because if I follow this formula, it's as if I thought about it as x to the 3 plus 1 over 3 plus 1, which simplifies nicely into this funny expression. Let's check it, okay? Now, if you're going to check it, you're going to have to rewrite it so it's easy to do in terms of derivatives. If I was trying to find the derivative of x to the 4th over 4, I might consider calling it 1/4 x to the 4th instead, you know. And now 4 times 1/4 is 1. And if I subtract that 4 minus 1, I get a 3, and I get this. Oh, look, I get x cubed, which is great. But here's where the little bonus trick comes in, and this is not very complicated, but you have to learn it up front, and then it's easy for the rest of the time you're doing integrals. Don't forget that if I was taking the derivative of this, and I got this, what if I took the derivative of this, but instead of it being that, it was this function? X to the 4th over 4 plus 71, right? What's the derivative of this function? The answer is, well, the derivative of this is this, like we said, and the derivative of 71 was nothing, wasn't it? Yeah, it's nothing. Well, how about any number there? Yeah, I could put any number there. I could put, for example, 3.14, one of your favorite numbers, right? Well, the derivative of x to the 4th over 4, that's x cubed. The derivative of 3.14 is a constant. Derivative of constants is 0, which just vanishes, right? So the point is, when you take the integral, and you're saying, what was that original function that I took the derivative of? There's not one function. There's infinitely many functions because it can be whatever you think, the x cubed, but plus any number would still yield back this as the integral. And so you have to think of it in that way that whenever you do any integral, you show that you recognize that n it could be plus a constant by writing plus c. Now, this is something that in mathematics, you see a lot of memes about it, and there's a lot of big jokes about don't forget plus c, and you do a whole long calculus exam, and you forgot to write plus c everywhere, so you got a 50, which you know is mean and all that. But the plus c thing is like a thorn in your side thing in calculus, and the idea of plus c is the connection between integration and derivatives. When you take the derivative of something, you can, and it has a constant in it, the constant vanishes. So if you're taking the integral of something, that original function that you took the derivative of it may have had a constant. And if it did, it could have been any constant. So to show that, you always write plus c. So the answer is really not what you're looking at here. The answer is this plus c. Now it's done. That's the correct answer to this question. All right. So if f prime of x is x cubed, f of x is this, and could have been plus 13 or plus 21, and the derivative would have been that back. Is the point. So based on that idea, now we have a general working knowledge of how integrals work. Let's do some examples and take a look at some important laws about integrals. The first one, of course, being the power rule that we're all familiar with, right? But now we're going to go in and show some other important rules. Here's some great integration formulas. I hope that when you're doing your practice that you'll come back here and take a look at these cases. I'd like to focus on each of them one at a time with you now. I'm going to look at the table on the bottom. These are just snapshot pictures right out of your textbook. All right, you can find them right in your book, or you could come back here to our PowerPoint and you could learn them. Let's talk about each of these now. The first one is that the derivative of x is 1. And since the derivative of x is 1, trying to get the highlighter out. Here it is. I'm talking about this idea. That connects with this concept. So I want you to try to remember that if you have the derivative of 1 dx, that's the same as saying that the derivative with respect to x of x. It's 1. Now look at this, at the rectangle on the right. The integral of 1 dx, that's the same as saying the integral of the derivative of x. It's going to be x. So in the integral and the d are very much inverses, and they literally cancel out, leaving just x. So I need you to remember that when you have nothing left in there, and all you have is integral dx, you can say that's x. So that aside, if we have a function that we take an integral of or a derivative of, like for example, x cubed, like we did before, if you wanted to, you could have the same idea as the constant rule applied, but in a backwards way in terms of integration, like this. In other words, when I had that case of the integral of x cubed, if it was the integral of 91x cubed, I could have forgot the 91 for a minute, done the x cubed, and then put 91 back on it later in the way that you see this c right here. So whatever that, I'm going to highlight it, whatever that coefficient to your expression, just kind of yank it out of there and put it out in front of the integral. And then you can forget about it and just work on the integral. All right, that's the constant rule, but for integration. All right, and then the last idea is the sum and difference rule that we've learned about, of course. The sum and difference rule says that if you want, you can take a sum and then take the derivative of each thing inside there. Likewise, with integration, that works. If you have an integral of many things being added up, you can take the integral of each thing. Please note, if you're going to act with the integral, it feels like the distributive property a little bit, but it's not. It's an integral law. If you're going to do that, please remember that when you do it, it is crucial that you do not just put the integral. You put the integral and the dx. And then for the next part, you put the integral and the dx for it. Remember that they are connected. It's kind of like they're like parentheses. If you put the first one, you have to write the second one. So don't leave them out in your writing when you're expanding integrals. Keep writing dx when you write the integral again. Right. So in reiteration, we have 3 important concepts here. Since the derivative of x is 1, it also serves that the integral of dx is just x. If you have a constant times a function and you take the derivative, you can forget the constant. Same way, if you have a constant next to a derivative and you integrate it, you can forget the constant. And last but not least, if you're taking the integral of an expression that has pluses and minuses in it, you can act as if you're allowed to distribute that integration to each of those different things and rewrite it and do each one separately in its own little way. Okay, got it? Those 3 important ideas. That's what we're going to focus on at first. Let's come back to, we have some cases here, and I'd like to go through how to do these. Now, before we employ all of those ugly rules, these 3 cases are great ways to express how to apply the power rule, which is the one that we just learned. So let's do a little bit of practice with that with examples 4, A and B, and with example 3. Start with example 3. Okay. So first we have example 3, which is saying evaluate the integral of x to the negative 1/2 dx. The key. So what does that mean? Well, recall the power rule for integration. Okay, power rule for integration, let's put it in a bubble up here. It's going to be the integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. There you go. That's the integration power rule. So this time n equals 1/2. So if n equals 1/2, let's think about this idea of n plus 1. What is negative 1/2 plus 1? Let's get some common denominators here. That's negative 1, and that's going to be 2. Remember that the number 1 can be expressed as anything over itself. For example, here, it's easy to join these two fractions together because 1 is 2 over 2. It's also 8 over 8 or 19 over 19. It's anything you want over itself, so use that. In calculus, as you could see, not only are you subtracting 1 for derivatives, when you do integration, you're often going to be adding 1. And when you add 1, it's to an uncomfortable fraction sometimes. Just convert your 1s into easy fractions that have the same numerator and denominator, and then it's very easy to add them. As you can see, the answer this time is supposed to be positive 1/2. Now, that's a little awkward, but we're going to put it all into place in the way it's supposed to be. Let me show you how it will be written out completely. It would start by writing it as x to the negative 1/2 plus 1 all over negative 1/2 plus 1 plus c. Then you try to simplify it. As we have determined, when you add these two, you get 1/2. So now it looks like this, friends. It becomes this, 1/2 over 1/2 plus c. Now, what does over 1/2 mean? Over 1/2 is the same as divide by 1/2, which is the same as times by 2, right? So why not just rewrite this to be 2x to the 1/2 plus c? And last but not least, you know what 1/2 means. X to the 1/2 is the root of x. So the answer here is 2 root x plus c. This is what they want. If ever they give you a requirement that you may not submit your answers with negative or fractional exponents, then you have to rewrite your math so that it looks like this with roots and fractions in it, so as to avoid giving answers with fractions and negative fractions. Now, in WebAssign, I don't think there's much of that. There might be some cases of that where it's on a lower level, but you see that as part of the study here when you're doing integration, that they have that as the formal way to submit your answers. Right? So keep that in mind, and let's get familiar with and well-versed with the idea of what x to the 1/2 means. It means the square root of x. Don't forget plus c. Right, okay. We have example 4. There's two pieces for example 4. Example 4a looks like this. It's the integral of the cube root of x dx. One thing I learned when you're doing calculus, don't write small. Cube roots start to get blurry if you write them small. Exaggerate and write them nice and big. Square roots too, make them big fat check marks, and then it becomes easier that way. And then little hints. I hope it helps a little bit. Well, let's start by looking at the power rule again. It says that the integral of x to the n is x to dx is x to the n plus 1 over n plus 1 plus c. Okay, we're going to use that, but first I don't like this root action. I'm going to have to convert it so that I could deal with it. So now this has become the integral of x to the 1/3 dx. Okay, same way that the square root is the 1/2, the cube root is a 1/3, and so on. The 9th root is 1/9, right? Okay. Now we're going to think about 1/3. I'm going to do some arithmetic over here, and I need to know what 1/3 plus 1 is, because if I let 1/3 be n, then it looks like this. It's going to be x to the 1/3 plus 1 over 1/3 plus 1 plus c, which means that I better make sure I figure out 1/3 plus 1 correctly. Let's do that on the side here. Again, 1 can be any number you like over itself. Why not make it 3 over 3 this time? So now you have 1/3, 3/3, and it adds up to 4/3. Don't hesitate. 1 plus 3 certainly is 4. Yes, it's 4/3. Improper fractions for exponents, why not? You're in calculus, of course. Of course, that's a natural thing. Don't think that, oh, I must be wrong. No, it gets very complicated sometimes. And this is actually a very practical answer in questions like these with integration. So yes, it turns out to be 4/3. Now, since it's 4/3, I can rewrite this to be x to the 4/3 power all over 4/3. What happens when you divide by 4/3? Over 4/3 is just like saying divided by 4/3. That is just like saying times 3/4. So can you remember that if you have a denominator with a fraction, That's the same as having a multiplier that is its reciprocal. Divide by 4/3 means multiply by 3/4. Now, if you wanted to really finish and write it so it had no fractional exponents, the last thing I would do is take this x expression and put it up there with the 3, because it is, after all, over 1 anyway. And then to handle these exponents, notice it's got a 4 as a numerator. That means that 4 is an exponent. And it has a 3 as a denominator. That means 3 is the index, and it has a root in it, looking kind of like this. Again, write big, because as you can see, it's kind of complicated, depending on how far you need to go. And by the way, don't forget that plus c. Don't forget it's also plus c to make it correct, plus c. Now you have the correct answer. All right. Example 4a is a great example because not only does it show the power rule, but it also shows one of those uncomfortable situations where you're in terms of square roots and cube roots and other kinds of roots, and getting familiar with the concept of how the numerator is just an exponent. That 4 became x4 in this case. The denominator is the index. The 3 here becomes the 3 inside the root check. So that's called the index, and that's how you can convert back and forth with them. What would it have been like if it was not this, but instead it was x to the negative 4/3? Then this whole thing that you see would just be on the bottom. That's what that means. And you have to get comfortable with how every number is a fraction. Every number is a fraction. And it's over 1 if you don't see that. So if you see something times x to the negative 2, it just means over x squared. And you have to get comfortable with that because they just keep on playing. That's what they play with a lot here when they do integration with the power rule. Example 4b is also similar. Now we're going to include the idea of that negative exponent. Example 4b looks like this. It's the integral of 1 over x squared. Now, like we said earlier, 1 over x squared means x to the minus 2. So this is really the same question as the integral of x to the minus 2 dx, like so. Okay, and we can use that important power rule that we learned today for integration. Remember, it looks like this. You're saying to yourself, he's writing it again. This is the 3rd time he wrote it. Yep, that's right. It is the 3rd time I wrote it. But notice it took me a total of 3 seconds to write it. And if you just jot it down, you'll start to remember it. You know, you should have it there and look at it and make it part of your process for getting this right. You should have it there as a model. It'll guide you and make sure you get it right. Right now, it appears x equals negative 2. So if I'm going to think about m plus 1, what is negative 2 plus 1? Think long and hard about it, friends. That is, after all, negative 1. Sure it is. Yep, negative 1. So that means when I do this, the actual algebra appears this way. And then that turns into this. Don't forget, of course, plus c. To make this a little bit more comfortable, 1 is the multiplicative identity. So when you divide by negative 1, the same thing happens as if you multiply by negative 1. Big secret, no one tells you that in math, but it's true. When you see divided by negative 1, you might as well just make it negative 1 times. And this negative 1 here means that it's over it. So this really is supposed to translate in this way, friends. It's supposed to look like this when you roll done. And the reason why is because this negative 1 becomes positive 1 when you make it a denominator. And this negative 1 is kind of like a multiplier of negative to change it to a negative expression or a negative quantity. And don't forget plus c. There it is. So what is the integral of 1 over x squared? The answer is negative 1 over x. All right, plus c, of course. So now that you have seen how those work, let's see if we can apply what we've learned to doing some more advanced ones. So just as a review, like we had said earlier, if you want to remember these ideas right here, you know, when you take the integral of just dx, it's x. When you take the derivative of, when you take the integral of just dx, it's x. When you take the integral of something and it has a multiplier, you can drag the multiplier out in front. When you take the integral of something that has more than one part being added or subtracted, you can integrate each piece separately. And now let's see if we can apply that to examples 5 and 6. All right, so example 5 is okay, great. Let's stop the share. Let's see now if we can figure out these questions. All right. Now, as we mentioned earlier, if you have a constant, you're allowed to take it out, right? And by the way, I forgot the dx's here when I was writing them down. Okay. All right. So in the case of part A, if you're going to pull out that 4, it would start by looking like this: 4 integral x dx. Okay. And now x is to the power of 1, right? Don't forget your rule. Your rule says that if you're doing the integral of x to the n, it's x to the n plus 1 over n plus 1 plus c. So this time it's 1. So shouldn't it be 1 plus 1 makes 2? It looks like this now. 4 times x to the 1 plus 1 over 1 plus 1. Which means 4x squared over 2. And of course, these knock out. So I have 2x squared plus c. Let's pause there for a minute and take a look at how that worked. The first thing I did was I pulled the 4 out, and that is the constant rule. Since there is a 4 being multiplied, and 4 is a constant, I can act like the 4 doesn't matter and put it out in front and just focus on the rest of it. Now it's x dx. The integral of x dx can follow the power rule because x dx is ultimately x to the 1 dx. Now, if n is 1, you can think about 1 plus 1 gives the 2. So the integral now becomes x to the 2 over 2. That's what I have written here in the parentheses. So don't forget the 4 is there. If I think about 4 times that quantity, I guess they cancel out like fractions, 4 and 2. And now you just have 2x squared left plus c. That's what we want for example A. In example B, it's a similar case. We're going to pull the 8 out first. Then we're going to apply the power rule to x to the 5th, thinking about n as if it was 5. So n plus 1 then makes a 6. That means that the integral here is 8 times the quantity x to the 6 over 6. And then these cancel out nicely. Don't forget the plus c. You can put it in at the end, but you should put it in as you go if you could remember is really appropriate. That would be 4x6 over 3 plus c. Okay. Now, when you're done, if you're not sure you got it right, go and take the derivative of it and see what you get. You should get x to the 5th, 8x to the 5th. If you did this, you should get 8x to the 5th. And you can check if you're taking a test before you turn in your answers. See what happens if you take the derivative of your answers till you get the original integrand back. Now, for this one, you'll notice we have a sum. So I'm going to start by writing this out as 2 separate integrals. The first one will be the integral of x cubed dx. And the second one will be the integral of 4x dx. All right. I'm a very big proponent of don't do the same work twice. So when we get to x dx, I already have the answer of x dx. It's x squared over 2. I'm going to just use that. I have that work right up here. First, let's do x cubed. We did x cubed. It was actually our first exercise of the night. Let's go get that for a quick minute. Here it is. All right. So if you do the integral of x cubed, oh wait, that's not it. Here it is. Sorry. So if you do the integral of x cubed, remember that we got this expression here? So that's the answer to the integral of x cubed. So I'm going to put that in this position. That quantity is x to the x over 4. It's x to the what? X to the 4 over 4. That's what this one is. Next, what is the integral of this one? I'm going to make this a 4 first. 4 integral x dx. And now I'm going to copy x to the 4 over 4. And now plus 4 times, and what is the derivative, the integral of x? We did that already. It's up here. It's x squared over 2. So we'll put x squared over 2 there. And then this simplifies also. So your solution is x to the 4 over 4 plus 2x squared plus c. I barely got that in there, but that's it. There you have it. All right. So when you find the integral, in this case for part C, you're integrating an expression that is a sum, and there's a plus there. So first, you take the integral of each thing separately. I wrote the integral dx for x cubed and for 4x. Here they are. Then I focused on each of them. This, you already saw the presentation of how to get that. It's supposed to give this. This one, I took the 4 out, so I wrote it once with the 4 out, and then I ignored the 4, and I did it. But we have the answer to that. The answer to that is actually right here. It's x squared over 2. I put that in. And then I simplified that into 2x squared, and now I have my solution. So doing these integrals, I recommend you use a pencil. I recommend you write big and get ready to make mistakes and try to figure out why didn't it reconcile, because the answers are going to be there for you. If it's supposed to be x to the 4th over 4 and you got x to the 4th over 3, you have to look at it and say to yourself, why did I get that? Where did I go wrong? Often we make very small mistakes. You know, most of the mistakes are right when you add 1. Like 3/4 plus 1 is really 7/4. And people will make a mistake and do it wrong because it's an easy thing, but if you do it so often, it becomes confusing and tedious that, you know, if you get lost, that's usually what it is, a small arithmetic mistake. Let's take a look at the next batch of questions. For example 6, we're asked to do the integral of x squared minus 4 quantity squared. Right. So take a look at this case. You may think about taking the derivative of it. That could be confusing, you know, because we're not doing the derivative, we're doing the integral. But if you did the derivative, you'd see that there would be some kind of chain rule action. In fact, you could probably see that all that we know really so far, the power rule of integration, the constant rule of integration, the integral of dx of integration, and we know the sum rule, none of them apply here because we have a weird case here. So for all intents and purposes right now, the way we're going to deal with this is we're going to just multiply it out. And then after we multiply it out, we'll do the sum and difference rule and we'll carry on from there. But please be advised, often when you see an integral of this nature, there's some kind of trick in it that you could do that makes it quick and easy. And when we get together tomorrow and we do substitutions and the chain rule, you'll see that come about. But for this, the way we're going to handle this is we're just going to kind of do brute force and go old school with the idea of how to square a binomial. Now, just as a reminder, how do you square a binomial? If you're trying to square a binomial, like a plus b quantity squared, the way you deal with it is you write it twice. So if you have a binomial squared, something like a plus b quantity squared, then what you should do is you should rewrite it so that it's written twice in a row like so and apply FOIL. The first idea is a times a, which is a squared. Then the outer is the a times b. And then the inner is, again, the a times b or b times a. And last is b squared. There are 2 of these. Oops, sorry. B squared. Now there are 2 of these. So it's 2ab there. The point, anyway, is when you have a quantity squared, what you should do is you should write it twice and square it. So let's do that for this. Okay. I'm going to rewrite it so that it looks like that. I'm going to multiply x squared minus 4 times x squared minus 4 dx. That's supposed to be minus, of course. All right. And then if we do that, first x squared times x squared, that's x to the 4th. X squared times minus 4 is minus 4x squared. Minus 4 times x squared is minus 4x squared. And last but not least, minus 4 times minus 4 is plus 16. Now, if we wanted to combine these two, it would become x to the fourth minus 8x squared plus 16 dx. Notice from here to here, we had to do some old 9th grade algebra rules. And now that we've done those rules, all you got to do is kind of apply the old rules that you've learned, the new rules that you've used, that you've learned about. For example, this one is a perfect candidate of the power rule. This one is the constant rule along with the power rule again. And this one is just an example of integral of dx, which will just become x. So let's take it from there. All right, so I'm going to now use the sum and difference rule by showing the integral of each of these three expressions. There'll be the integral of x to the fourth dx plus the integral of negative 8x squared dx plus the integral of 16 dx. Okay, so all I did was I just split them. When you split it, don't forget to put dx on it every time too. All right, let's take constants out. This one has no, coefficients, not constants, coefficients. Let's take coefficients out. This one has no coefficients. I'm just going to rewrite it. This one has a coefficient of negative 8. This one has a coefficient of 16. Now, each of these cases is a power rule. This case is the other rule that we haven't used yet, which is the identity fact that the integral of dx is just x. Okay, so let's use those now. For x to the fourth, it ought to become x to the fifth plus x to the fifth over 5. Now minus 8 times, and this is going to be x to the third over 3. Plus 16 times, and now the integral of dx we have learned is just x. Simplify a little bit, might be a little bit better to put this over 1 and put these together. Final answer looking like this: x to the fifth over 5 minus 8x cubed over 3 plus 16x, and then of course don't forget at the very end your plus c. You can put the plus c all in throughout it as you go. Or you could put it in at the end or whatever, but just make sure your final answer has plus c. All right. And so that was example 6 for you guys. Let's take a look now at what's next in our lesson. So let's do an application. Remember the expression marginal. What does marginal mean? Well, in the same way that the margin is the slope, remember the slope and the derivative are related. So if you know a function like the revenue function or the cost function or the profit function, and you want the marginal profit function, then you take the derivative of it. Likewise, if you have the marginal function and you want the original function, you take the integral of it. So for example, if you have the marginal revenue and you'd like to know what that original revenue was, you can find it if you integrate it. So when you integrate a margin, you get back to the original function because a margin is just a derivative. Let's read example 7. It says, sales records at Gyrus Technologies show that the rate of change of the revenue, that is the marginal revenue, in dollars per unit for a motherboard is shown with this expression, with this equation. They're using MR with a bar on top to represent the marginal revenue, where X represents the quantity sold. Find the total revenue function for the product, and then find the total revenue from the sale of 1,000 motherboards. Okay, so now you're looking at a practical application. Let me jot down the actual marginal revenue, and then we'll go from there. When we're done finding the original revenue function, we're going to carry on by finding the original revenue at the sale of 1,000 motherboards. First, let me jot it down. The marginal revenue, this is example 7. Marginal revenue is given as 300 minus 0.2x. All right. So if you'd like to find the original revenue function, R of x, the way you're going to find R of x is by integrating the marginal function, which means whatever that is, dx. So that means you're trying to figure out this now. Now notice I'm using parentheses because this is a binomial. If you don't put parentheses, it doesn't look right. Okay. Now, the first thing I'll do here is apply the sum and difference rule, and I'll put the integral on each of the two expressions there. So it becomes the integral of 300 dx plus the integral of minus 0.2x dx. Now I'll apply the coefficient property, which says that if I have an expression that starts with a coefficient, I can take it out of the integral and ignore it for a minute while I focus on the actual integral, then multiply it later. In this case, the first one I see is 300. And the next one I see is 0.2. All right. Now, this right here is one of our rules. The integral of the derivative of x is x. And here we have a constant. And remember, we did this already. The integral of x, because it's x to the 1 power, is actually x squared over 2. We have it in our work back there somewhere. But it would be like this, x squared over 2. And then if we simplify that just a little bit, the 2 and the 0.2 cancel out. It would be, if you canceled out, 0.1. So it would be 300 x minus 0.1 x squared, and plus c, of course. All right. Yeah, I had to think about that one for a minute. That one kind of confused me a little bit. But yeah, when you divide by 2.2, yeah, okay, I don't know why that kind of slowed me down a little bit. That's what will happen after you keep doing calculus for a long time. You'll start to look at basic things and say, wait a minute, what is it? 0.2 divided by 2 is, of course, 0.1. I had to think about that one. Anyway, this is what we're looking for our solution. This is ultimately right here, your revenue function. Now, if you'd like to find out what the answer is in the specific case where you have 1,000, what you do is you put 1,000 in that position for x and get your solution. That's just a matter of putting 1,000 right here and 1,000 right there and getting a calculator out and figuring out the answer. I'm not going to drag you through that. I know you know how to substitute in the value, and that's what they're going to want for an answer like that. All right, now, let's talk about differentials. Differentials are those small pieces that we discussed earlier that go at the end, like right here when you had dx, that was a differential. Differential has a specific direction. It tells you which one to use, whether you should use y or you should use x. So if y equals f of x is what you have, then dy equals f prime of x dx. In other words, if you have a specific case where they tell you to find dy or to find du or to find just d something, they're not exactly saying find the derivative of this or find the integral of it. It's kind of delicate what they're asking for, and they want your answer to be a new differential. So if you want dy, you have to solve it as if dy was part of a fraction. Let me explain what I mean. Example 1, you have a question that says, find dy if y equals x cubed minus 4x squared plus 5. So the way you're going to do this is you're going to go in and you're going to take the derivative. And you know how to do that. That's an old skill that we've learned. Well, we're in a summer course, so we learned it 2 weeks ago, but you would feel like in a semester, well, we learned that months ago. So you take the derivative, okay? I'm going to write it, instead of writing y prime or f prime of x, I'm going to write dy dx. And I know just what that is. It's easy to find. It's 3x squared minus 8x. And the derivative of 5 is nothing. We've done that many, many times. But now that I'm through with this, I'm going to put this in parentheses like so, and I'm going to multiply both sides, just different color for that, by dx, like so. And when I do that, look at what I get. The dx's cancel out. And I have a new statement that says dy equals 3x squared minus 8x dx. I want you to remember, friends, when they give you a specific question that says find dy, if y equals all this, then find dy dx. And when you're finished, present your answer like so, with dx at the end of it, in the same way you would have written the derivative that way. Let's do one more example from our PowerPoint, where they ask you to figure out, find du if u equals 5x to the 4th plus 11. U equals 5x to the 4th plus 11. Okay. So let's see if we can find du. Well, I have u and x, so let's find du dx. Du dx will be 20x cubed plus the derivative of 11, which is nothing. To figure out now what is du, I will multiply both sides by the dx. And I have a new statement that says du equals 20x cubed dx, like so. So this is what we mean by differentials. The reason why it's so important is because we're going to learn now how to apply the chain rule in terms of integration. And for the chain rule, the idea of u or u substitutions comes into play because you're taking new expressions and finding powers of them. All right, so let's take a look at some cases like that then. The power rule with u substitutions works like this. If you see an expression that you're integrating that looks like a big expression, but it's all to a power, it's the same idea as the chain rule. It's just a matter of making sure you use the derivative of what's inside. The derivative of what's inside better be there. And if it's not, then you can't do it. For example, take a close look at example 2 with me. Can you see, looking at example 2, that if I design the whole integral such that this is u, can you see that the derivative of u is right here? Look, here's the derivative of u right here. So you have to look for it. It should be right there in there with the integral. And the reason why is because you can rewrite this integral so that you have differentials involving a new letter u, so that you can kind of get shortcuts. Now, if you want, you could do this the hard way. You could multiply out 3x squared plus 4 times itself 5 times. You could employ Pascal's triangle. You could do a lot of ways, do a lot of things to get that. And it's really a tedious, ugly process. And chances are you'll make a little mistake somewhere with your arithmetic. But, you get the same answer. And here in quantitative analysis, we're trying to find those shortcuts and those quick, direct ways to get answers. In a case like this, the way you should deal with it is look at the integral and see if you can tell that the derivative of one thing is actually right there next to it. In fact, to make it really easy on you guys, in this one, it's right next to the dx. Look at what happens if you just take the idea of making that expression 3x squared plus 4 into u. Let me jot it down first. Example 2 is the integral of 3x squared plus 4 quantity to the 5th times 6x dx. So if you're trying to find the integral of this thing, notice that it looks like something to the 5 power, which is something I'm familiar with, power rule. And the derivative of what's inside, the chain link that we like to talk about for the chain rule, is actually present. It's right here. Let's start with a statement that u equals that expression 3x squared plus 4. It follows then that du equals the derivative of this dx. Now, if you wanted to, you could have written this first and then written that. But after you start doing your substitutions, you get used to it. You kind of go from here to here. And again, it follows that idea of our last example where we had differentials, right? So if this is du, then I can just replace this whole thing with du. And if this is u, then I could just change this whole thing with u, which means that my new integral is actually really very basic. It's the integral of just u to the 5th du. Look how simple that became. So the whole point of the u substitution and employing the chain rule is to make it that you rewrite an expression, but also take care of all those little nuances of, but wait a minute, the chain rule says the derivative of what's inside of blah, blah. Okay, the derivative of what's inside is here. Now how do you do it? So they set them up to be collapsible, that the derivative is there. And if you're very careful and you state u, and you put that in the place of u, and then you state du, and you put that in the place of this, it turns out to be something really straightforward and simple like this. Let's find the answer. The integral of u to the 5th du is going to be u to the 6th over 6, because of our power rule, plus c. What was u? We already made up u. U is right here. So the new thing actually reads, it's going to be that expression 3x squared plus 4 to the power of 6 all over the number 6 plus c. There you go. That's what we wanted for your answer. So this is what we mean, friends, by u substitution. You look at the integral, it appears that it looks like some expression to a power. You change that expression into the u, then you do the integral. You find du, dx, you do the derivative, and you hope for the differential to be present in the integral, and it is. 6x dx is there in the integral, you can see it there. And so you switch everything out in terms of u so that you have a new integral, but it's just in terms of u. And then when you have that, you can integrate that, just thinking of the letter u. And when you're through, come back and change u into what the expression was that you substituted for it. And now you have a final answer. Let's do a couple of examples of it, and it'll become clear how that works. All right, first one, example 3, is the integral of 2x plus 3 under a root times 2 dx. Okay. So I don't like the square root. I'm going to rewrite it right now to look like this. Great. Now, if I think of this as an expression to a power, it then serves that u equals 2x plus 3. And if u equals 2x plus 3, I may assume that du equals 2 dx. Okay, I'm going to talk about this for a minute. The derivative of 2x plus 3 is going to be 2, because 2x, the derivative of that is 2, and 3, the derivative of that is nothing, so it's just 2. So you could say du dx equals 2, or you could say it this way, du equals 2 dx. And I need to say it that way because now I can see that du is this thing right here. And I can see that u can be replaced right in here, like that. So I can rewrite this integral now to be the integral of u to the 1/2, and then this is simply just du. See how perfectly it boils down? It always comes down to something very simple that way. Next, let's do the actual integral. We've already done this one, but let's do it again. U to the 1/2, recall, 1/2 plus 1 is like 1/2 plus 2 halves, and that's like 3 halves. So this has just become u to the 3 halves over 3 halves. This is where the doubt creeps in. Don't let the doubt creep in. It's just fractions, and you're in a great class. You know what you're doing here. So what does it mean divide by 3 2's? It means multiply by 2 3's. And what does 3 2's mean? Well, the 2 means the square root, and underneath has a 3 as an exponent. Last but not least, what is u? U is this expression 2x plus 3. So the final solution is 2 square root of 2x plus 3 quantity cubed all over 3 plus c. Don't forget plus c. Don't forget plus c. And that's what we need for that. Again, you could see that the derivative of the expression is right there, is 2 dx. They're making it clear for you. Don't worry, soon they won't make it clear, and you'll have to use your math wit to figure out what it could be. The next case is the integral of, and I'll write it here. Example 4 is the integral of x cubed times 5x to the 4th plus 11 to the power 9 dx. Okay, so now, for the first time, you're going to see a little bit of variation with the du and the dx, and you're going to see a little bit of a constant fraction situation happening because it doesn't match exactly, but we do have a match in terms of powers. For example, when I take this being u, and I say, okay, I'm going to make u equal 5x to the 4th plus 11. By the way, a mention here, guys, not to the 9th power, just the expression, because the 9th power has to stay there when I have u to the something. I have to have u to something. It's going to be to that 9. So I'm not putting 9 here. That's a very common mistake. You put the 9 there. Don't put the 9 there. But if you do that, it then serves that du is going to be 20x cubed dx. And it does come back that at least we have x cubed here. But notice we have 20x cubed. So how can I fix this? Well, the way I'm going to do it is first I'm going to rearrange this so that it looks like this. Okay. And then I'm going to rearrange this cleverly so that it looks like this. 1/20th du equals x cubed dx. So this is 1/20th du now. And this right here is just u. So it becomes the integral of u to the 9 times 1/20th du. Okay, let's stop there for a minute. Take a look at how I wrote that. 1/20th is a good example because 1/20th is such a strange quantity. Notice we have in our derivative for du that uncomfortable 20. You just solve it the other way around and you have an expression for x cubed dx that you could switch in there. And that whole expression, however ugly it is 1/20th over du. Friends, remember this fraction? You will see cases with odd fractions like this very often in u substitution cases with exercises with u substitution. The fraction is kind of the focus of it, and it always boils down to make sure you do this part right. Because now they're all multiplied together, u9, 1/20th, the differential du. You can use your commutative property and move them around as much as you want, but 1/20th ultimately becomes a coefficient. So you can pull it out and put it in front. Now it looks like this. 1/20th. Oh, sorry. 1/20th, let me put it here. 1/20th, the integral of u to the 9 du. Okay, so let's take it from there now. If it's 1/20th times that, then it looks like this. Let me jot it down again. 1/20th integral of u to the 9 du. And we know the power rule. It should be 1/20th times u to the 10 over 10. You might feel tempted to say, wait a minute, they cross out, don't they? No, they don't. And they will try to tempt you. Watch out. They've come up with numbers that make you feel like you should cancel out. In this case, you do not cancel out. 20 times 10 makes 200. And yes, that looks funny, but that's what you're supposed to do. Be careful with your counting techniques, friends, okay? And last but not least, if I have 1 over 200 u to the 10, I remember earlier I designed this so that u is this expression 5x to the 4th plus 11. So it's really 1/20th times 5x to the 4th plus 11 to the to the 10 plus c. That was example 4. Example 5 looks like this. It will be the integral of 5x squared times the root of x cubed minus 4 dx. Once again, you're in a situation where you see that the derivative of the thing inside at least is the next power down. From x cubed, you take the derivative, you would get something of an x squared, and x squared is there. So I'm going to rewrite this right now to look like this. I'm going to pull the 5 out, and I'm going to use fractional exponents to express this root. And then I'm going to include x squared dx there like that. So no, that's supposed to be a minus in the middle, but I think you guys get it. So see what I did? I pulled the 5 out, and likewise, I rewrote it with an exponent that's comfortable, and I moved the x squared piece over by the differential so that I could think about if I have du, what dx would be and how I could modify it so that it becomes x squared dx. Let's let this be u. Remember, when you do this, don't use the exponent, just use what's inside. So x cubed minus 4, that implies that du equals 3x squared dx. But I want x squared dx, so I'm going to have to divide by 3, which brings me to the idea that 1/3 du equals x squared dx. Okay, so for this piece, I'm going to rewrite 1/3 du. For this piece, I'm going to put u. It ought to look like this. 5 integral u to the 1/2 times 1/3 du. Not very hard. Bring that 1/3 out in front, and now you have 5/3 integral of u to the 1/2 du. Let's take that from the top. 5/3 the integral of u to the 1/2 du. How do I integrate that? Well, recall 1/2 plus 1. And by the way, didn't we do this? Do I have to do this yet again? I did it. If you did it and you have the answer, go back and get the answer. Why do it again and again? Here it is. Here it is right here. When I did u to the 1/2, which I've done that already, this is what I get right here. Let's use that fact. Okay. 2 root u cubed over 3. 2 root u cubed over 3 times this quantity 5/3. And then that's 10 root u cubed over 9. U is supposed to be x cubed minus 4. So this just became equals 10. X cubed minus 4 quantity cubed with a root all over 9 plus c. There you go. We want for that one. So can you see that what's happening is they're playing games with the fractions with the du. Do you remember how to multiply 5 times 1/3? Do you remember how to solve for u to the 1/3 and so on and so forth? It's the same stuff over and over. That was example 5. Let's skip to example 7 because example 6 is a little moot. We're going to go right into example 7 now. Example 7 has 2 parts. This one is example 7a. We're asking to evaluate 2x squared minus 4x quantity squared times x minus 1 dx. Now, for this question, I'll warn you, we might have to do the F word, factoring a little bit, just so that comes up. But what happens is these exercises guide you through all different avenues of math, like fractions, like radicals, like factoring. Different old topics come up, and it's kind of like you have to be on your toes when you're in calc to be able to accomplish all these funny questions that are all different. It's a wide range, like a wide gamut of different kinds of math ideas that show up when you try to solve these questions. Starting with, if you look closely here, it appears that u could be what's squared there, which is the quantity 2x squared minus 4x. Let's see what happens when we just jump in and say u equals 2x squared minus 4x. Then du becomes 4x minus 4. Now, I wish I had x minus 1 dx. Don't forget, by the way, that is dx, my bad, that is dx. But I have this. And you'll notice it's actually really not that far off. So let's just mess around with it and factor it and see what happens. If you do, you can pull out a 4 and look at how you get exactly what is in there. You get exactly what's in there. Let's divide out the 4 so that I could say that du over 4 is the same as this quantity. Okay? And the reason why I want to do that is because I also want to show that u is the same as this quantity right here. So now what's happening is I have simply du over 4, or 1/4 du in that position, and this is the u. I'm going to write it in black across the top. So it should be the integral of u squared times 1/4 du. To make that just a little nicer, it's 1/4 the integral of u squared du. I want you to remember, when you figure out all the hard part of du equals what dx and what to substitute where and which one works with that, it always boils down to a simple power rule case like this. And then when you do your work, you do the power rule and then you come back, you put x in there and you have your solution. Don't forget plus c. So let's take that one from there. 1/4 u squared du. If I took the integral of that, with n being 2, that would make it 2 plus 1 makes 3. So that would be 1/4 times u cubed over 3, which is the same as u cubed over 12. And now u is x squared minus 4. And don't forget your plus c. All right. So it was there. It was just a little bit hidden with factoring. But once we factored it, it did become very clear what to do next. Right? And bring it over by dividing. Let's do another case. 7b is just like that. Let's do 7b. Example 7b is integral of x squared minus 1 over x cubed minus 3x quantity cubed dx. All right. Man, this one's pretty ugly, isn't it? However, let's start by writing it in a way that's easier for us. I'm going to change it so that it's not over that expression cubed, but it's times that expression to the minus 3. That's the same idea. So let's write that out and see how that feels first. I'm going to make this into the integral of x cubed minus 3x to the minus 3. Isn't that the same as if I put it in the denominator? And now I'll show that I mean to multiply it by x squared minus 1 quantity dx. All right. So let's jump in with our idea of the u substitution. If I let u be this expression here, is it possible that the derivative of it kind of looks like this? The answer is yes, because if this is x cubed, the derivative will be 1 degree lower. This is x squared. So it probably will work. Let's start by writing out u equals that and see what the derivative turns out to be. We could say u equals x cubed minus 3x. And then it follows that du equals 3x squared minus 3. Didn't really explain that very much because I know you all know derivatives, but the reasoning is this is, of course, the power rule. 3 comes down and we lower it, comes 2. The derivative of a constant times x is just what that coefficient was. And this is our derivative. Don't forget it is dx, of course. Now, this does not look like that. But if I factored it, would it look like that? Yes, it would. Let's factor it. It would be 3 times x squared minus 1. And then to isolate it, I could divide by 3. Which means that now I have evidence that 1/3 du is x squared minus 1 dx. So if I took this and put it up here, the new thing would look like this. I could take this and make it 1/3 du. And I could make this u, which makes it the integral of u to the minus 3 times 1/3 du. And then the constant rule says you could take that 1/3 out. All right. Again, I've boiled it down to something that's very simple. It's just u to the -3. And ultimately, that's really kind of all we got is just that power rule. And then some little rules like we showed earlier, like the coefficient and all those others. So let's take it from there with u to the -3 and find the integral of that. It ought to be 1/3 integral of u to the -3 du. -3 plus 1 is -2. So this ought to be 1/3 u to the -2 over -2, which is something like this. To make it a little bit nicer, you could make it like this, 1 over 6u squared. But it's not u. What is u? U is x cubed minus 3x. Plus c, of course. And there's your answer for that one. The next one is an application. Let's look at that one together. Okay. This is our last exercise tonight. Thanks for your attention, friends. Let's close with this one. It's an application involving a marginal revenue function. It's just identical to the last application we had where there was a marginal revenue function, except this time, when you take the integral, you'll wind up with a u substitution case. Suppose that the marginal revenue for a product given by this expression is given by this expression. Again, we have MR bar, which is the marginal revenue, and we have an expression. Now find the total revenue function. What that means is go ahead and integrate it. Okay, so if we want to integrate it, here's what we'll get. Example 8. We have the marginal revenue function is given as 600 over the square root of 3x plus 1 plus 2. All right. If you'd like to find the revenue function, you'll have to take the integral of this with respect to x. So the revenue function can be found if you integrate the marginal revenue function, dx, which would look like this. Okay. Now, first of all, even though it's a little ugly looking, it is ultimately a sum, right? It's the integral of the first ugly fraction, but then plus the integral of 2 dx, you know. So first what I'd like to do is split them up. And I'll make it equal to, and also I'm going to take care of this. That means an exponent of -1/2, right? So we're going to write this as the integral of 600 3x plus 1 to the -1/2 dx plus the integral of 2 dx. Now, this is just going to be 2x, right? But when I do this, I'm going to first take the 600 out. And when I do that, just watch out because now I let u equal what's inside. Okay, let's just recap. So far, this is where we are. We have, for the first one, 600 times the integral of 3x plus 1 to the -1/2 dx. By the way, we also have plus 2x later on because we did the integral of 2 dx. I'm just going to kind of put a little bubble around that, all right? So let's let u equal what's in here. It serves then that du equals 3 dx. And I can now assume 1/3 du equals dx, which means that this right here should be replaced with 1/3 du. So I'm going to rewrite it now to be 600 times the integral of u to the -1/2 du times 1/3. Now I could take 1/3 and multiply that by 600, and it's 200. All right. Oh, I didn't realize I was off key there a little bit. There you go. Okay. So Let's now find the integral of u to the negative half. We did that somewhere along the line, didn't we? Yes, we certainly did. Let's see, where did I do that? Well, wherever I did it, let's do it again. All right. So that's going to be 200 times u to the positive 1/2 over 1 over 1/2, because negative 1/2 plus 1 is 1/2. So divide by 1/2 is like times 2. So now it looks like this: 200 root u times 2, which is 400 root u, and u is 3x plus 1. Don't forget that last piece, which was plus 2x, and don't forget plus c. So your final answer: 400 root 3x plus 1 plus 2x plus c. That is your original revenue function. Now, gone through a lot of them with you. I could see that's a lot of math, right? Yeah. That's all we've got for you guys today. I sure do appreciate your close attention to my lesson. But let's talk for just a minute about what's coming forward. In the future, when we get together tomorrow, Thursday, we're going to do chapter 12.3 and also chapter 13.2, which is definite integrals. It's just an application of what you learned. Right now, there are 2 exercises in WebAssign for you to complete, and this exam will only have 4 sections, the 2 I just went through with you, and the 2 we're going to study tomorrow. Your exam is scheduled for Monday. If you have questions about any of the WebAssign and you'd like to meet, just send me an email. I'm happy to meet with you, and we could study together on Monday. Until next time, my friends, we're going to stop our recording, and then I'll open up the floor to questions. Thanks again for your attention. Have a great night.